this out of here. A system of solving equations is just what that sounds like. A system is just a group of equations. We need for more than one answer, or I'm sorry, we need for an answer to work in more than one equation. It's not just when does x become greater than 5. There's sometimes multiple things that are going on. Now, my guess is you're going to remember a lot of this from Algebra 2 days. I'm going to kind of go through it with some speed. But if I say something that you're not sure about, slow me down. Let me back up and say it again. And just watch this one for a second. One equation. Y equals 2x minus 3. Y-intercept of 3 down here. Y-intercept of 3. Negative 3, slope of 2. So I go up 2 over 1, up 2 over 1, up 2 over 1, etc., etc. And each point on this graph, if I were to pick any point, there's one. If I were to pick any point and plug it into that equation, it should work. So this is the point, negative 1, 1, 2, 3, 4, 5. So this is the point, negative 1, negative 5. And that should work in the equation. So when I plug in negative 1, I get negative 2 minus 3. By golly, I get negative 5. That's what a graph is. It's a picture of all of the solutions. There's an infinite number of solutions, not just the integers, all of the points in between the integers too. This is this point right here is 1.7.1 maybe. I don't know, I'm making that up, right? But there's a point there that's some decimally thing that would work in that equation. That's a picture of all of the points that work. Here's another equation. That's a picture of all of the points that work in that equation. And so if I were to pick some random point off of that line, it should work in that equation. So, what's a system? A system of equations is just a bunch of equations. In this case, I got 2. And the solution, so, how many points are in the blue? Well, there's an infinite on the blue. There's an infinite number of them on the red. But how many are in both? Just 1. And that's what we're finding. When we're solving a system of equations, we're finding that point, at least when it's 2, that works in both of them. That's the key point. Now, what I've just done is solved this system of equations graphically. You draw the graphs, see where they overlap. You have to draw them with enough neatness that you can see where they cross, right? If you're a sloppy drawer and you kind of got them going zigzaggy, not so well. So draw them neatly enough that you can see what's going on. I will ask you on a test or quiz, solve this system of equations by graphing. That's all you do. Graph the lines, make sure they cross the point. Easy to check. Take the point 2, 1, plug it back into the 2 equations. It better work. If it doesn't work, you messed up somewhere. That's what solving a system of equations about, finding the solution of multiple equations. That's all we're doing. Now, as we advance along here, we're going to solve bigger and bigger systems. My friend who was working at GE, he was solving systems of equations that had 17, 18 equations with 10, 12 variables. Now, he didn't do it by hand. They did it on the computer. But we're going to do things by hand so we understand the concept behind what's going on so that if at some point in time you do some engineering, you understand the premise of what the computer's doing for you. Right now, we're going to talk about 3 different ways. We just solved by graphing. We're going to solve by elimination and by substitution. If I give you a system of equations, one system, like I just had a graph, right? If I give you a system of equations, you should be able to find that solution any of those 3 ways. And sometimes I'll ask you to find it all 3 ways. Oh, by the way, the answer's the same for all 3 of them, right? If it's the same system, you better get the same answer. If you don't, you messed up, right? There's one solution for a system of equations like that. And so what I'm looking for is technique. Can you solve it this way? Can you solve it that way? Can you solve it this way? It's going to be the same. Sometimes I'll tell you the answer. The answer is 2, 1. Show me how you get it now. So solve by graphing. Again, you just watch this one. You don't need to write this down. But what's a real key thing that I'm going to want to do here? So what do you think? Put it into slope-intercept form. Because that's the easiest way we know about how to graph a line. Now, nicely, these are lines. When we advance through some stuff and we get into the calc next year, we're going to be doing some curves and finding intersections of curves and how to solve those, and we'll get to that. So I got the two lines in slope-intercept form. Graph one of them. Here's the red guy, y-intercept of 7, slope of 2. Graph the other guy, y-intercept of 4, slope of 1/2. You got to draw them neatly enough that you can see where they cross. That's all that's involved. Nothing, no rocket science there, or jet engine science. It's pretty straightforward. That's my graphing. Okay. So as I said, a solution should work in both equations. Don't need for you to do this, but you can if you want to. All I did is I took, what was the answer? -2, 3. I took -2 and 3 and plugged it into the first equation. I put -2, 3 into the second equation, and they work. They give me solutions. I get some true sentence. 0 equals 0, 3 equals 3. Those are true. So they're solutions. All right, so second way. Okay. And I will have a, I'm going to test a quiz. I'm going to say, solve this system of equations. I'm going to have a space that will say graphing. We're supposed to graph it. That's kind of obvious. But there's going to be two places, one for elimination, one for substitution. Know which name is which. I'll give you most of the credit if you accidentally reduce them, but I'll probably yank you a point or two. Know which name is which name. It's not a huge deal, but know the vocabulary. This is elimination. And think about what the word eliminate means. We are eliminating or getting rid of one of the variables. Now, ultimately, that's kind of what happens in both of them, but it's the process that you use to get there. Elimination works this way. I took this equation and I rewrote it like this bottom one. I took and brought the 2y over to the other side, and then I multiplied it by -2. How come? What do you think? Well, and so what I'm going to do, because I got two x's, now I could have dealt with the y's as well. I could have fiddled with these y's and made them do the same thing. But what's going to happen is when I bring this other equation over here, 2x plus 4y, I'm going to take 2x plus 4y and add it to this side of the equation. There it is, 2x, or -2x, sorry, -2x plus 4y. If I add something to the left side of the equation, what do I have to do to the right side of the equation? Add the same thing, right? But I don't want to add the exact same thing, but I want to add something that's equal to it. So what I'm going to choose to add to the other side is 16. How do I know that -2x plus 4 is equal to 16? Because that's what it says it is. That equation we just had a minute ago said that -2x plus 4y is the same as 16. So on the left side of this equation, I'm adding something. And on the right side of this equation, I'm adding something. And when I add those things together, because of the work I did before, I have, here comes the fun word of the day, eliminated. Thank you very much. The x's. Okay. Does this kind of sound, look, feel familiar from some days gone by? I'm hoping that it's back in there somewhere. That's elimination. Arrange one of the equations, and sometimes you have to arrange both equations. Sometimes you might have to do something to both of them to get one set of variables to cancel each other out when you add them up. And so I made it so that the x's cancel each other out. Could have done the exact same thing with the y's. I could have multiplied this guy by 4 up here so that the y's could have canceled out. Ooh, that got big. I messed with the x's. It's your personal choice, whatever your preference is. So by eliminating the x's, I'm now able to solve for y. Y equals 3. Ah, now that I know what y equals, I can go back in and figure out what x is equal to. So I take that value of y equals 3, go back into either equation, doesn't matter where. Go back somewhere, plug it back in. So plugged in y is 3. Simplify. Right? Hello. Hello. All right. Okay. Let me take a deep breath there. So the final solution here for this thing is -2, 3, which I probably have on the next line. Yeah. That's the solution. Yay? Nay? Yay. All right. Sorry. Substitution. Where'd it go? Where'd it go? There it is. Substitution. Hey, guess what? It's the same system of equations, isn't it? Guess what the answer is? It's the same. If it's not, you messed up. But now I'm looking for a different process. So, here's the premise of substitution. Solve one of the equations for one of the variables. Ooh, well, one of them already is solved for one of the variables. Solve one of the equations for one of the variables. I solved this equation for x. Well, it already was solved for x. And so look what this says. It tells me what x is equal to. X is equal to, well, not a number, but it's equal to some other thing. And since I know what x is equal to, I can, here comes the second fun word of the day, substitute it into the other equation. And the key phrase there is the other equation. It's got to go into the other equation. You put it back in the same equation, everything will cancel out. You're left with 0 equals 0. So solve one of the equations for one of the variables, substitute it into the other equation. And look what that does. It makes, look at that. That's pretty good, isn't it? So I'm putting it in for x. And hopefully it'll stop in a minute. There it goes. And now what I've done by that substitution is made it so there are no more x's. I've got an equation only in y. Listen to why I said that. Only in y. So, distributive property. Distributive property leads me then to second line, third line, with only y values in it. Solve from there. Now that I know what y is equal to, ding, 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 I should be able to go figure out what x is equal to. Hey, it's the same answer. I must have done it right. That's substitution, that's elimination. Go have a conversation with this guy. Hello, little friend. Yeah. He'll come back down in a minute. Or he'll go away. All right, those are the 3 ways I'm going to ask you. Next quiz we have, absolutely, we'll have a problem just like that. It'll give you the same system, show me all 3 ways. Same answer all 3 times. So what I'm grading is the process, the work, not just the answer, right? I really kind of sort of don't care about the answer. Well, kind of I do, but, okay? Second idea here, third idea, some idea, fourth it says, but a different idea. When you solve a system of equations, and we're talking about lines, if these are linear equations, lines can behave one of three ways. They can behave one of three ways. They're either going to be parallel to each other, or they're going to touch each other somewhere. If they touch each other just once, you get something that looks like that, or they could touch each other a whole bunch of times. The right two have a solution. These two have a solution. If they have a solution, we say it is a consistent system. A consistent system has an answer. So that very first problem we did was a consistent system. But because there's two kinds of consistent systems, we need a second word to describe what kind do we have. So the problem we did a minute ago where there was one point where they intersect, that was a consistent independent system. It's a consistent independent system. Consistent means there's an answer. Independent means the two lines are independent of each other. Where this one goes doesn't affect this one. The second option is when it actually ends up being the same line right on top of each other. That means any point that works in the first one works in the second one. Any point that works in the first one works in the second one. If there's no solution, you got parallel lines, they're inconsistent. And then there's no second word because that's all you got, inconsistent. You know what it looks like. So these guys over here, you would need to describe with two words. Consistent dependent or consistent independent. Guy on the left, inconsistent. It's not really the end. Let me show you an example. I'm going to give you one more little piece. If I had 2x plus 4y equals 8, and I had x plus 2y equals 4. So maybe you can glance at that and tell me what kind of system it is. What do we got here, Brother? It's consistent dependent. Because what you've got here is the exact same equation, right? But sometimes equations are very, I don't know, I've made it real simple, right? I just made it up off the top of my head. So sometimes you can't tell. So here's what's going to happen. What I want to do is kind of show you what would happen if you didn't recognize that off the top of your head. And you still can write an answer for this. And I'll show you what I mean. So let's say we're going to solve this by substitution. So I got x equals negative 2y plus 4. I'm going to take what x is equal to, and I'm going to substitute it in over here, 2, and then negative 2y plus 4 plus 4y equals 8. So a little distributive property. Four y's go away, and I get 8 equals 8. Now look what happened. All the variables canceled out, and what was left is true. If all the variables cancel out and what's left is true, you've got a consistent dependent system. That means the two lines are right on top of each other. Now, I don't know what this looks like. Let's do a quick graph of this thing. Let's say, so I subtract x and divide by 2. I'm going to have y equals negative 1/2 x plus 2, right? So 1, 2, slope of negative 1/2 looks like that. How many points are on that line? Infinite number of points. And so by golly, if I did the same thing to this equation, it would look like this. Be right on top of it. We'll pretend it's right on top of it. How many points are on that line? Infinite. How many points are on both lines? But it's not just any point. I can't just say any x and any y. That point will not work. So here's what you need to do to show the solution. This equation is y equals negative 1/2 x plus 2. Go away. Ah, see, snuck in on me. Negative 1/2 x plus 2. So here's how you show the answer. You would say it's a consistent dependent system. Look what this says that the y value is. The x value is this, and what's the y value? So that's a way of showing the solution. Now, it's not a specific point, right? Because it's an infinite number of points. But what this is saying to you is that any point that makes this true is going to be on the line. Any point that makes this true is going to be on the line. I could have used this. X plus 2y equals 4. So that problem's done. I'm doing it a different way. So I could have said this. I don't know what the y value is, but the x value is negative 2y plus 4. And so any point that makes that true is on the line. So what you're doing is you're expressing the solution in terms of the variables in the equation. Either of those would be acceptable ways of writing that answer. So you would say this is a consistent dependent system, and you could write either one of those as a solution for that. Now we'll go with the end. That's it. Rest of the time, yours. Start on homework. 2.1.